This is the term project presentation of Group D, consisting of Ben Moyer, Ziyu Xia, and Alex Pershala, and our topic is wind turbine efficiency. For our Measurements 2 term project, we were tasked with the design and execution of an experimental setup. We would do this in order to verify an equation, take measurements, and or perform an analysis on a system of our choice and our design. The purpose of this, the goal of our setup, was to use the measurements of wind speed or wind velocity, current drawn and voltage measured across, taken from a scaled down wind turbine model in a controlled wind tunnel environment in order to calculate and compare values. These values would be of theoretical power defined as 1/2 rho AV cubed, rho being the density of the air, A being the circular area swept by the fan blades in the form of pi r squared, and wind velocity cubed multiplied by a half constant. We would compare this to the observed power output, which is defined simply by the voltage measured multiplied by the current measured. By placing these in a ratio, we will derive an efficiency value for the wind turbine model, the purpose of which would be to observe changes in power generation capabilities of the system as a result of changed parameters, which will be elaborated upon further later on in the presentation. Now, the general formula for any efficiency value, eta, which is the fancy looking n you see there, is defined to be the observed value divided by the theoretical value. This will get you a numerical value less than or equal to 1 being a perfectly efficient system and 0 being a system which has no value whatsoever. The goal of the analysis of this given system would be to optimize in turbine, or eta, which is P observed divided by P theoretical, by the changing and the tweaking of certain parameters within the system to optimize this and thus extract the maximum power from a given system, a given area, given wind speed, etc., and so forth.
What we've done is we made our own wind turbine. It is constructed by a DC motor and a 3D printed fan holder. The 3D model looks like this. And then we put our wind turbine to our wind tunnel. One thing to be noticed is that the wind tunnel provides its sweep frequency. And by using this sheet, we can transfer the frequency into the wind speed. That's how we get our wind velocity inputs. Then we connect our wind turbine to the circuit. Our circuit looks like this. It has a load to consume the energy generated by the wind turbine. And by switching these two switchers, we can use a single multimeter to measure the voltage and the current go across this load. And here we have a short video to demonstrate how do we do the whole experiment. We put our wind turbine to the middle of the center of the wind tunnel to avoid turbulent flow. And here is this path shows us the sweep frequency. And now we start the whole wind tunnel. We need a few seconds to wait for the wind tunnel to speed up. So there is going to be a flow go through here. And because the sound is very loud, we just mute the whole video. Now it starts spinning and we wait until it goes to a stable state. First, we use the multimeter to measure the voltage output. Then we switch the switchers, change the circuit, and measure the current output. Well, here's the data we get from the experiment. We have 5 trials and our efficiency is about 0.167%. It's very low, but I think by following the same procedure of testing, we can get the efficiency of different wind turbine, and by comparing them, we can get some conclusion.
Now that we've had some time to reflect on our experiment, we've derived some pros, cons, and conclusions to encapsulate the experiment as a whole. For pros, we determined that the setup was very simple to make for us. It's pretty easy to understand for laymen or people who don't know what's going on electrically. It's really easy for us to get accurate readings, and the data is really ready quickly. In terms of cons, we have an inefficient motor. We have an inability to take continuous data, that is discrete data points, and it is an issue that it requires a large and expensive wind tunnel, which kind of bars the entry for people trying to do this at home. In conclusion, we found that we would need to get a more efficient motor, we would need to try out different blade designs and sizes, and use Arduino-based sensors to get a more accurate and better reading overall. One concept that we would like to highlight from our experiment is a formal design of experiments. In this design, we are using a 3-variable, 2-factor formal design of experiments. A variable, in this case, is a way of defining how many changes you want to make during your test. For our example, we use swept radius, blade angle, and motor type. In terms of a factor, we used a 2-factor formal design of experiments, which means that it's the number of trials within a variable that define all the options for the test. In this case, we use 2 factors, so we have a +1 term and a -1 term, which means we have 2 different ways that we can change our variable to include in our end-up testing subject. In terms of the final project, we have test numbers on the left-hand side of the chart that define the number of tests that we do to completely encapsulate the full variable set. The number of tests that we use ends up being 2 to the n variables, where n is the number of variables. So if there's 3 variables, we need 8 tests. If there are 4, we would need 16. We also define each of these factors as a -1 for one of them and a +1 for the other one, and then disperse them out for each test so that every combination of the test is completed overall. Thank you and have a great day.